So, how do we actually measure the mass gain or loss of a continental ice sheet? Well, there are three basic methods. The first involves directly measuring dH dt, the left-hand side of the mass balance equation, the rate of change in the ice surface as a function of time. Now, the measurements of ice surface elevation can be straightforward enough, but if you want to convert that into a mass loss or mass gain, you have to worry about density. If the change in surface elevation is due to surface processes, changing snowfall or changing surface melt, things of that nature, the appropriate density to use is the density of snow or firm. If the observed thinning or thickening is due to dynamic processes, that is ice flow stretching or compressing, then the appropriate density is the density of ice. And those densities differ by a factor of 3. The second method involves the two terms on the right-hand side of the mass balance equation, the flux and the source term, that is the accumulation and the melting. So for that method, you need to measure the surface snowfall rate and the surface melt rate, and you have to measure the ice velocity and the ice thickness and multiply them together and get flux. Now we can measure ice velocity at the surface directly using satellites, and we can measure ice thickness using radar. But then there is some uncertainty in the velocity structure with depth, whether the surface velocity goes straight down or whether you have some type of internal deformation. In addition, there can be uncertainties involved in the measurement of accumulation and melting. Actual in situ measurements are rather sparse. As you can expect, I mean, the interior of a continental ice sheet is very remote and it's a difficult location to work, so there aren't that many measurements. And so you have to either interpolate between existing field measurements, perhaps guided by satellite measurements, which use the field measurements as ground truth, or use some type of climate modeling. The third method involves gravity. Now, when an ice sheet gains or loses mass, this actually affects the strength of the Earth's gravitational field over the ice sheet. And this can be measured, and it has been measured. The chief sources of uncertainty in this is what's called glacial isostatic adjustment, GIA for short. Basically, the ice sheets were a different size 15 or so thousand years ago. In the last glacial maximum, they were quite a bit bigger. And so this weight depressed the surface of the Earth. You had a huge ice sheet over North America. Greenland was bigger than it was. Antarctica was bigger than it was, or than they are now. And when those ice sheets shrank, or in the case of North America, completely melted, the Earth's surface has rebounded. And so you have flow within the Earth's mantle. And this density imbalance can show up in a gravity signal. So to remove that, you have to have some model of the glacial history and of the viscosity of the Earth's mantle.
The paper we're going to look at in this video is by Rignot and his colleagues, and they found that not only are Greenland and Antarctica losing mass, but that the rate of that mass loss has been accelerating. Now they use both the second and the third methods, and what they found was that in 2006 the combined mass loss was 475 plus or minus 158 gigatons per year. So the rate of mass loss was several times the uncertainty. And that also the total acceleration in mass loss was about 36 gigatons per year squared. Now this chart is from their figure 1, and it is their actual data for the second method. And we could see that discharge, which they call D star, the star meaning that they've corrected it for changes in the grounding line position, and the grounding line being the spot where an ice sheet goes afloat, has been steadily increasing since the data set begins in 1992. Whereas surface mass balance, which they call SMB, and surface mass balance is the net between surface snowfall accumulation and surface melt in the summer, so I've labeled it as net snowfall, has been decreasing. In other words, melt has been getting higher and snowfall has been getting lower. Or at least snowfall is not increasing as fast as melt rate has. And of course, this means that round about 2000, it looks like, the ice sheet began to lose mass. And if we look at their data for Antarctica, here we see a similar pattern. Now, their figure 2 is where they difference those two numbers, surface mass balance and discharge, to obtain net total mass balance for the ice sheet, and where they compare this to the results from gravity, what I called method 3. And as you can see, round about the year 2000, the net mass balance of the ice sheet went negative, and it hasn't been positive since. Now in this figure, the black dots with the gray arrow bars are mass balance from the second method, and the red dots with the red arrow bars are mass balance from the third method, that is from gravity. And you can see that the data coverage extends a good deal further back in time for surface mass balance and velocity measurements, but that the two methods agree pretty well with each other. They lie more or less on top of each other, and also their trends, that is the acceleration in mass balance, the acceleration of the mass loss from the ice sheets, also agree within their uncertainties. If we now look at Antarctica, we see a similar story, except that in Antarctica, the mass balance went negative very close to the start of the record in about 1994, and with the exception of brief spikes that have occurred roughly periodically since then, it has remained negative. And just like in Greenland, the rate of mass loss has accelerated. Again, you can see the gravity data lie pretty close to the surface mass balance and discharge data, with the exception of a brief period in 2008, and that also the trends, that is the acceleration in mass loss, agree within uncertainty. If we then look at their part C of figure 2, which is the sum of the two ice sheets from the surface mass balance minus discharge method, we see that as a whole, the Earth's continental ice sheets have been losing mass for almost the entire period for which data exist, and that the rate of mass loss has been increasing. Bad news for people who live in coastal places. Now, this is only one paper, of course, and one paper cannot be the be-all and end-all of all knowledge. But this one paper is representative of what the data are showing, of the results that are being presented in the scientific literature on the polar ice sheets. The polar ice sheets are losing mass. This is consistent with a warming climate. It's also consistent with a climate in which the warming is concentrated in the polar regions, as very, very early models of climate change predicted it would be. Something called polar amplification. Now, people can spout off all sorts of cockamamie theories about how scientists are waging a conspiracy to deceive all of humanity and, I don't know, further their solar panel agenda. But this is what the world is doing. The ice sheets don't care about our political issues. The climate system does not care about our political issues. All it sees is more greenhouse gases in the atmosphere. And all the ice sheet sees is higher surface temperature, higher ocean water temperature, and more melting.